So far, we've talked about transforming data through linear transformations. The idea of a linear transformation is that you're shifting and rescaling the data. So, for example, you're multiplying some x variable by a constant, and then you're adding a constant. The most common linear transformation is the z-score. We like z-scores because we can take different x variables and put them on this common metric with this mean of 0 and this standard deviation of 1. And then we can compare, for example, different values for, example, ACT and SAT scores. You can compare them. We like linear transformations for that reason. Another kind of transformation is a nonlinear transformation. We use nonlinear transformations when we have some sort of nonlinearity or skewness in a set of data, and we want to remove that nonlinearity so we can apply some kind of measure, such as covariance or correlation, that assumes linearity and that only can capture a linear relationship in a set of data. Just like we have linear transformations and we see linear transformations all the time, you also might have encountered nonlinear transformations. Here are some examples of nonlinear transformations. So if you have some x variable and you want to transform it in a nonlinear way, you can take the square root of x. You can take what's called the logarithm of x. You can take 1 over x. In each of these cases, we're changing the actual shape of x and creating a new variable called y. And we typically do this when we want to straighten out some kind of nonlinear relationship or some kind of skewed relationship. To put another way, the idea is that we want the distribution to be more symmetric. We want to reduce the presence of outliers or skewness. This is very important because a lot of models are based on the mean. Covariance and correlation are in essence models. They're measures of association, and they're based on the mean. So if you have skewness or nonlinearities, they can be very misleading. We transform data using these nonlinear techniques, these nonlinear transformations, all the time. The most commonly used nonlinear transformation is a logarithm. A logarithm, what is it? Well, it's a logarithm. You have some x variable. It's a nonlinear transformation. A logarithm, all it's doing is it's answering a particular question. It's telling us how many values of a particular number do we have to multiply to obtain another number. So for example, how many values of 2 do we have to multiply to get 8? Right? Well, 2 times 2 is 4. 4 times 2 equals 8. So we can say 2 times 2 times 2, or 2 to the third power, equals 8. Thus, the logarithm is 3. So we can say that we can write this as of a log of base 2 of 8 is 3. Okay? To reiterate, the logarithm of 8 with a base of 2 is 3. All we're doing is we're taking this value of 8, we can call that the value of x equals 8, and we're in essence changing it to an exponent. And that exponent is based on 2. Right? All we're doing is we're saying how many values of a particular number do we have to multiply to get another number? Well, you must multiply 2 3 times, 2 to the power of 3, to obtain 8. That's all a logarithm is doing. And a logarithm, by doing this, it's a nonlinear transformation. It's, in effect, changing the distribution of a set of data. And we see logarithms used a lot. For example, some variables, such as income. Income is often logged because the distribution of income is nonlinear. There's a certain amount of skewness because you have a small number, for example, the United States with a lot of money. We have this sort of high level of wealth inequality. So the distribution of income, we often log it. There are lots of other variables that are logged too. For example, population, if you look cross-nationally, we often log that variable. But the idea is this is a nonlinear transformation It reduces skewness often, and it can also be used to make a set of data more linear, so we can use covariance and correlation. And we typically don't use a base of 2 when we construct logarithms. The most common bases for logarithms are 10 and e. This is also known as Euler's number. This is a constant. It's just like, you can think of it like pi. So Euler's number e equals 2.718 roughly, within rounding. And we use these bases because they have certain desirable mathematical properties. The key point here is that these bases of 10 and e, they're very common. So for shorthand, if you don't see a base mentioned, log without a base, it usually refers to a logarithm with a base 10. And then we use ln, or the natural logarithm. That refers to a log of base e. So you can see that if somebody says, oh, I did a natural logarithm of an x variable, that usually refers to a logarithm with a base of using Euler's constant of roughly 2.718. Again, when we think about linear transformations and nonlinear transformations, it's nothing too abstract in the sense, you've seen linear transformations before. How many cents to a dollar, Celsius versus Fahrenheit. You've also seen nonlinear transformations before. You've probably talked about metrics that are based on logarithms without even realizing it. For example, the Richter scale, which is used to measure earthquakes historically, it's on a logarithmic scale. One property of a logarithmic scale is that by changing x to what are, in essence, exponents, right, we're reducing the skewness, but jumps in the scale have different sort of jumps on the raw scale. So the Richter scale, an increase from 1 to 2 versus 8 to 9. Well, the jump from 1 to 2 in the raw scale is actually pretty small, whereas an earthquake between 8 and 9, right, that's actually a huge difference. That's a property of the fact that the Richter scale is on a logarithmic scale. They do this so that the that the sort of whole set of values is compressed, and so that in essence, to reduce skewness. Another sort of common nonlinear pattern has to do with Moore's law, and so we're going to look at Moore's law to think about what it means to do a nonlinear transformation. So Moore's law is based on the computer scientist Gordon E. Moore. He worked at Intel, and in 1965, he noticed that the number of transistors on a microchip, they were increasing exponentially, meaning they were increasing in a way that was doubling every 2 years. So year 1, if they had 2 transistors on a microchip, right, 2 years later, they would 4 transistors, and then they would have 16 transistors on a microchip, and so on and so forth. And when you plot this kind of pattern over time, you have this highly nonlinear curve. What's interesting about Moore's law is that some people consider it a very important sociological and technological trend, because this idea of Moore's law, it's increasing computing power in a way that's really has drastically transformed society. And Gordon Moore, he thought that this trend wouldn't continue after maybe a couple decades, but it's continued well past the 1970s. But the key point for our purposes is that this distribution is highly nonlinear. So this is Moore's law. On the y-axis, we have the number of transistors counts per microchip, and on the x-axis, we have year. So this goes from roughly an early period up until roughly the current period. And on this curve, we have different data points. These are different kinds of microprocessors, rather. And for our purposes here, you can see that this doubling effect, it doesn't appear as much at first, but eventually this doubling effect is having this huge change. So currently, with Moore's law, the number of transistors are doubling. And since the actual number of transistors is quite large now, that doubling is really having this huge effect in terms of the raw transistor counts. The problem with this distribution is that it's highly nonlinear. One way to think about it is there's sort of outliers with respect to the x variable. You can think of, on the left-hand side, you have this long tail. You can think of that long tail as outliers. And it's also kind of difficult to read the graph. If you were to apply a covariance or correlation to this scatter plot, you would get a highly misleading value, because that correlation is going to try to fit, it's going to try to capture a linear pattern. But this is a nonlinear pattern of the data. It doesn't approximate a straight line at all. It approximates this sort of curved line, right? This curved relationship in this set of data. So what can we do to, if we wanted to, for example, apply covariance or correlation to this data set? Well, we can do a logarithmic transformation. We can do a nonlinear transformation. What this is going to do is it's in essence going to change our values to exponents based on whatever our logarithm is. So here's Moore's law. It's the exactly same pattern, but it's on a logarithmic scale. All we've done is we've taken the y-axis and we've logged these values with a base of 10. Right? And you can see here that we have the same sort of data points, but as we move up on the scale, on the y scale, we can see that the jumps are actually much greater and greater and greater. But this is useful because when we have a logarithmic transformation, we can, in this case, you can see that we could apply covariance and correlation quite easily. There's no sort of problem because the pattern, the relationship between time and this outcome, it now approximates some kind of linear pattern. So we could use covariance and correlation. But just to be completely clear about what's going on, all this is, it's a nonlinear transformation. So here we have C as the number of transistor counts, right? And we're just taking the logarithm of that, and we're obtaining these new sets of values. So a logarithm, so suppose you have 10,000 transistor counts, that's the raw value. You take a logarithm of base 10 of that value, and we get a new score of 4. Okay? If we take a value of 1 billion, we get a new value of 9, and so on and so forth. The key point here is that what we're doing, in essence, is we're taking these raw scores and we're changing them to exponents. And you can see that, between 10 and value of 1 million or billion, there's a pretty big jump. But then you can see that even though we have these huge increases in our raw scores, the exponents, they don't change that much. And that is the effect of making the data, the distribution, more symmetric. And it also makes it so that there's not this skewness that we have with the original set of data. So in essence, we can think of this logarithmic transformation as a nonlinear transformation that's changing the shape of the data so that we can use it in ways that are consistent with our statistical techniques, such as covariance and correlation. So just to summarize, linear transformations, we like them because they change the mean and the spread. Okay, you're shifting and rescaling the data. Shifting in terms of the mean and rescaling in terms of the spread. But we're not fundamentally changing the shape of the data. The most common linear transformation you'll encounter is called the standardized score, or the z-score, or sometimes just the standard score. What this does is that when you change some x variable to a z-score, right, the z-score has this nice property of having a mean of 0 and a standard deviation of 1. So your x variable, when transformed to z-scores, it tells you how many deviations above or below the mean a particular score is. So we saw with ACT and SAT scores that one student was 2 standard deviations above the mean and another student was 1 standard deviation below the mean. So we can compare these 2 different values on a same distribution. Nonlinear transformations, in contrast to linear transformations, we're changing the shape of the data. And we use nonlinear transformations when we want to make the data more symmetric, to reduce skewness, to reduce nonlinearities, so that we can use metrics such as covariance and correlation. There are lots of nonlinear transformations, but the most commonly used nonlinear transformation, arguably, is the logarithm of a variable. You can have many different bases for a logarithm, but the key idea of a logarithm is that you're reducing this skewness and the presence of nonlinearities by transforming some value into a different scale. And this new scale is based on some x. You're basically transforming x to some kind of set of exponents. And these exponents are based on whatever the base of the logarithm consists of. The overall point, however, is that nonlinear transformations are very useful and very commonly used. And so in practice, you will use them time and time again. And with that, we will conclude our discussion of transforming data.